You cannot patent potassium carbonate. It is a basic mineral salt. It has existed in nature since before recorded human civilization. No corporation can own it. No corporation can charge you monthly. No corporation can sell you a subscription to a mineral compound. So the industry did the only thing available to them instead. They buried the knowledge. They removed it from education programs. They replaced it with planned obsolescence and replacement cycles. The average American spends $3,000 per decade replacing appliances that a $1 mineral would have saved. $3,000 per decade per household. Multiplied across 140 million American households, that is $420 billion in preventable waste. That is the number the appliance industry needs you to forget. That is why potassium carbonate is not on the label of anything. That is why no appliance manual ever mentions water chemistry. That is what they have been hiding since 1950. The information was never secret. Here's what should make you genuinely angry about this. The information was never secret. It was published and verified. Beckman published it in 1924 in peer review. The Water Research Study confirmed it in 2006. New Hampshire researchers confirmed the findings in 2011. 3 independent sources across 8 decades of consistent hard data. Not one appliance manufacturer ever printed it in a user manual. Not one hardware store ever placed it near the washing machines. Not one major home improvement show ever mentioned it. That is not an accident. That is an industry decision, a choice. How to do it yourself. Here's exactly what to do starting this weekend in your home. First, locate the water supply line feeding your washing machine. Turn off the machine and pull it slightly forward from the wall. You will see a hot water inlet hose and a cold water inlet hose. Go to any grocery store or pharmacy and buy potassium carbonate. It is also sold as pearl ash or potash in the baking section. One bag costs between $1 and $3 at most stores. Add 2 level teaspoons directly into the drum before any laundry. Run a standard full hot cycle with no clothing inside the machine. The potassium carbonate dissolves into the water supply immediately. It raises the water alkalinity to a pH of around 11 to 1. At that pH, calcium and magnesium compounds cannot form hard crystals. They remain dissolved and flush out completely through the drain. The existing scale on your heating elements begins to soften down. Within 3 to 4 cycles, it releases fully from the metal surface. After 30 days, your machine runs under measurably reduced strain. After 60 days, the bill for that appliance drops noticeably lower. After 90 days, the heating element reads within normal range. For your dishwasher, add 1 level teaspoon to the detergent compartment once per week. For your water heater, dissolve 4 teaspoons in a full pitcher. Turn off the heater power, attach a garden hose to the drain valve, drain 3 gallons out, then pour the pitcher into the cold inlet. Turn the water heater back on and run a full heating cycle. Repeat this entire process once every 3 months. The average American water heater costs $200 new. This treatment every 3 months extends its functional life decades, not just years, for just $12 total over 20 years in mineral powder. A repair technician charging $200 per service visit who replaces your water heater every 8 years earns $4,000 from your household over a 20-year period on average. This powder costs $12 over that exact same 20 years. The knowledge survived. This knowledge did not disappear because it stopped working. It disappeared because it worked too well for too many households. Potassium carbonate kept every appliance running when the industry needed those same appliances to break on a predictable schedule. So they removed it from every manual, every training curriculum. They repackaged it in expensive desk-cooling products at 50 times the real cost and hid it behind brand names no one connects back. But the mineral itself never changed. The chemistry never changed. The same 2 grams per cycle that Beckman confirmed in 1924 still works exactly the same in your machine today. That knowledge survived because some people refused to forget it, and now you are one of those people. You cannot unknow this. What you do with it next is entirely up to you. The Amish Revelation, redefining infrastructure. The road into Lancaster County doesn't prepare you for what you're about to see. Rolling fields stretch to the horizon. Horse-drawn buggies move steadily along narrow roads. There are no utility poles carrying high-voltage lines into massive treatment facilities. No pumping stations. No computerized control rooms. No miles of underground sewer infrastructure costing taxpayers millions of dollars every year. Yet, hidden behind one modest Amish farmhouse sits a waste treatment system that challenges nearly everything modern society assumes about sanitation. I first noticed it because there was almost nothing to notice. A shallow gravel trench disappeared quietly into the landscape. No machinery hummed in the background. No electrical connections fed pumps or aerators. No warning signs marked a complex industrial process. And perhaps most surprising of all, there was no smell. This simple system handled the waste generated by a family of 8. No odors, no swarms of flies, no visible contamination, no mechanical equipment, Standing there, it was difficult to reconcile what I was seeing with the reality most Americans know. In many communities, households pay hundreds of dollars every year to remain connected to municipal sewer systems that require constant maintenance, specialized operators, chemical treatments, and expensive infrastructure upgrades. For the average homeowner, a sewer bill of $600 per year isn't unusual. Yet this Amish family's annual maintenance cost was estimated at roughly $50. That difference raises an uncomfortable question. What exactly are we paying for? The answer becomes even more surprising when you trace the system back to its simplest form. Long before gravel trenches and biological filtration beds, the Amish approach begins with something that appears almost primitive: a small wooden privy and a bucket. After each use, a layer of sawdust is added. To most observers, the idea sounds unsanitary. Modern culture has conditioned us to believe waste must be immediately flushed away using gallons of treated drinking water. But the Amish method follows a completely different philosophy. Instead of treating human waste as something to be hidden and transported elsewhere, it is viewed as a biological resource entering a carefully managed decomposition process. Inside the composting system, naturally occurring microorganisms begin their work. As oxygen circulates through the material, microbial activity generates heat. Temperatures rise into what scientists call the thermophilic range, a level high enough to accelerate decomposition and suppress many harmful organisms. Over time, the contents undergo a remarkable transformation. The recognizable waste disappears, the odors vanish, the material darkens. What remains resembles rich forest soil more than anything most people would associate with a toilet. The smell, according to those who work with the process, is closer to damp woodland earth than sewage. At first glance, it feels impossible. But the real surprise isn't the simplicity, it's the performance. Because hidden inside this low-tech system is a number that demands attention: 98%. That figure represents bacterial removal rates observed in properly functioning biological treatment processes, using principles remarkably similar to those found in some of the most advanced wastewater treatment facilities in the world. In other words, a process built from wood, sawdust, microbes, and patience appears capable of achieving results that begin to approach the standards pursued by sophisticated industrial plants, costing millions of dollars to construct and operate. If that sounds unbelievable, that's because it challenges one of the most deeply rooted assumptions of modern infrastructure: that effectiveness must always be expensive. And that raises a larger question. If a simple biological system can deliver results this impressive, what else might we have overlooked in our pursuit of increasingly complex solutions?